We have seen how to calculate the electric field and potential due to an electric dipole. However, in many materials, you will find that there are molecules which are, although electrically neutral, but have some kind of dipole moment like H2O. It is having permanent dipole moment. Okay. Similarly, there will be molecules of like CO2 and some molecules which will have a dipole moment which will appear whenever the material is placed in an outside or external electric field. So in that scenario, how to calculate the effect of these things, these dipole moments which are present in the material? So let us see how. We will try to describe multipole expansion, which is a concept which will be utilized whenever we need to find the electric field and potential due to a collection of molecules or charges up to a certain level of accuracy. Let us say this is a material and it is formed with molecules which are having some dipole moment and charge like this. Let us say let us say this is the qith charge and we want to calculate the field at this point P. So let us say this is R, this is Ri, and the location of this charge is Di. So let us say I make a perpendicular here. Now we want to calculate the field at this point. One thing is that we can do what we can do. We can take 1 by 4 pi epsilon naught outside and try to do this sum from I is equal to 1 to all the molecules or the charges. Now, if this R is very very far away as compared to these molecules and their distances, so we can see that this R is going to be quite equal for all the charges if this point is too far away. So what we can do, we can take this R also outside. This Ri will be approximately equal to R and I will just sum over this. But you see, we are now in a bad situation. This total charge, as I already told, that this material is electrically neutral. So this is going to give you total potential 0, which is of course quite okay if you don't want very accurate results. So this material is of course going to behave as electrically neutral at very far away points, but we need to do something better than that. So how to go about it? So we will further try to refine using Taylor's series expansion. So what we will do, you see that this Ri can be written as approximately R minus this portion, and this portion is, if this is di, so this is di dot ar, so this will be Ri. So what will be 1 by Ri? Will be 1 by R 1 minus di dot ar over R. Now, since this is smaller than 1, this quantity is smaller than 1, I can use approximation. 1 by Ri is equal to 1 by R 1 plus di dot ar over R. Now continuing this thing in the next slide, we can see that potential at this point P is 1 by 4 pi epsilon naught Qi over Ri, and we know that I can write Ri 1 by Ri as Qi 1 by r plus di dot ar over r squared, and further more terms. Of course, next term will be r cube, like this. So you see, I can write it as 1 by 4 pi epsilon naught summation qi by r plus summation qi di dot ar by r square summation qi some term over r cube. So now we know qi di is simply pi. So you see, 1 by 4 pi epsilon naught, this potential will be, now this is the first term which we saw, which went to 0, but we want further accuracy. So let us say we will consider this. So it is simply pi, or if this is going to give total dipole moment, so p dot ar over 4 pi r square. So you see that if you want further accuracy, we will need to have dipole configuration approximation. But let us say the material is made of such molecules which have further weaker dipole moments. So we will need to have this further term, and this will be similar going to 0, like this. For further accuracy, we will have to take further expansion, and that's why this kind of expansion of series is called as multiple expansion, or sorry, multipole expansion. So this term was because of not considering any dipoles. This was because of dipoles. This will be because of quadrupoles. And in this sense, we can further refine our calculations if we want to perceive the effect of various poles, dipoles or quadrupoles, which are going to be created because of the material being put in external electric field. So you see that in this way we can refine our calculations, and this technique is sometimes used whenever we want to get good calculations. And from this we have seen one more thing. What is this thing? That the potential of a normal charge falls with 1 by r, a dipole falls with 1 by r squared, a quadrupole, it will die with 1 by r cube, so on. So from this we can clearly see that we need not solve any numerical examples for quadrupole. We can easily find that for the quadrupole, this field or potential is going to decay with 1 by r cube. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and join our Telegram group for doubt discussion, whose link is given in the description of this video. Thank you.